Thank you. In other words, we will have a look how to adjust the configuration DNS to make it more suitable for actual real operations. We will begin with short overview of the previous work on this topic, focusing on the behavior of time-to-live values in DNS. Then we will look at our little lab experiment to see what happens if we seriously shorten the TTLs, and then compare the experimental results with the real-world experience from a real TLD. First, and most important thing is that the TTL value is always wrong. The number is always either too small or too long. If it's too small and the servers cannot get answers to clients, then it will expire, data will expire from caches, and everything starts falling apart. If it's too long, we have seen what happens with Slack and .nz. About that case, we will hear more tomorrow in this very workshop. So pick your poison, basically. Another problem is that TTL in DNS doesn't really behave as we expect. Sometimes it can be stretched like semi-legally with the serve style feature, and sometimes it's just weird, and resolvers do weird things like either shorten it or prolong it very long. There is, again, previous work on that topic. In the slides, you can find clickable links. Blue text on the slides is always a link leading to previous work. And also tomorrow, there will be yet another presentation on that very topic named the role of DNS in the residential internet use. So we've established that it's really hard to tell what's going to happen until you try. Some big operators actually did change TTLs at large scale, so we can learn from their experience. One of the recent cases was the RIPE-NCC, which went from 2 days to 1 day in case of NS records, and for DS records even shorter. So the theory would predict approximately doubling the number of queries seen on the TLD, well, the authoritative servers. But that's not what happened. In practice, there was absolutely no difference. If you click on the link in the slides, it will lead you to RIPE-NCC's presentation, where they conclude that changing the TTL didn't have any effect. We can argue, okay, maybe 2 days were too long to start with. Maybe there is some like typical default limit in the resolvers. And if it's above, say, 1 day, it's too much and it will get shortened anyway. But CZTLD as yet another example, went from 5 hours at the beginning to 1 hour. And it was a couple of years back. So now we can tell that it didn't make any change whatsoever on the query rates seen on the authoritative side. If you click on the link in the slide again, it will get you to their article. If you really closely look at the slides, you can see for yourself that the numbers didn't change. That was the past experience, which tells us that going from 2 days to 1 hour doesn't really change anything on the authoritative server, which is, I would say, at least counterintuitive. Now, the question was, can we go to even shorter values? If we were discussing DNS issues in the past again and again and again, and the recurring theme is that the DS record had, or DNS key, had too long TTL. So when something went sideways, the operator couldn't actually react fast and fix the problem on spot because they had to wait a couple of hours until it expired. So the lab experiment is focusing on DS and DNSKEY record types. And we've implemented little TTL limit in the resolver. So inside the resolver, we limit the TTL for these 2 record types to 5 minutes. If it's longer, we cap it at 5 minutes. If it's shorter, we keep the original value. And then we look at the latency on the answers visible to the end clients and the queries to the authoritative servers and count what happens on the authoritative side. Just for reference, in the slides, you can find a little patch for bind code base, so you can try it yourself. The experimental setup is very simple. On one machine, we have software called DNS Shotgun, which is acting as a DNS client and simulating the query load as it was in the real. Second machine is bind, talking to the real internet. So we get the real behavior of authoritative servers and, of course, real noise from the internet. So we repeat the experiment 10 times for each configuration and then evaluate the results. For getting realistic results, it's very, very important to use realistic data set. So to start with, we've got a data set from a telco in Northern Europe. And that was a PCAP from a single resolver inside the telecom network, of course, anonymized. And we've replayed the traffic. Here, it's important to note that it was in the Northern Europe. And that's well known in this community for having lots and lots and lots of signed domains. So the TLDs, which are very popular in there, have over half of the domains actually signed. So if there was any effect, we should be seeing it. Just to underline the point that we are using the real data, not like artificial test query set. This is the query rate as seen in the PCAP we are replaying, and you can see on the y-axis query rate with 100 millisecond resolution for the single box we were replaying from. And there are wild jumps all over the place, weird variations with like 11-minute period. What is that? How that come to exist? But that's the real traffic, what we can do. So this is what we replay. Again, just to underline the point, we have all the weird clients in the data set as well. We have some clients which send 1 or 2 queries within 1 hour period of the test, then like the normal clients in the middle, and then the weird clients which are talking all the time to the resolver on the right side. But that's just to illustrate that we are using real data. Finally, we are in half of the talk, and we finally go to some results. This is the latency histogram. You have seen it a couple of times, probably in the previous OARCs. The y-axis is response time in milliseconds. X-axis is percentiles of slowest answers. But here, for purpose of this specific talk, we don't really need to really even understand the axis. Because if you look at the lines, there are 2 lines. One is the blue for the original bind, which is behaving as standard specified in the protocol, so the TTL is being followed. And the orange line on the other side, which is for the hacked version of the resolver, which is limiting the TTL to 5 minutes. And the point is that the lines are so close that you cannot even tell a difference very often. We had to repeat the experiment 10 times to see whether it moves a little bit or not. But it turns out that the difference between the orange and blue, so the original and the hacked version of the resolver, is within the measurement error. It's just the noise from the real internet because we are benchmarking against the real network. So it turns out that the limiting TTL to 5 minutes for DS and DNSKEY records doesn't really change anything whatsoever on the latency. And this chart shows result for 1 hour period. So maybe someone could argue, okay, maybe there are some little differences and bumps which get averaged out during the 1 hour, so we cannot see it. So to verify that, we have looked at the 5-minute window from minute 5 to minute 10, which is exactly the period where the TTL limit kicks in. If there was something long with TTL longer than 5 minutes, the cap would limit it to 5 minutes, and it should be expiring in this time window. And again, the orange line for the TTL limit in effect and the blue line for the original version of the resolver are overlapping all the time, and all the differences are within measurement error. So really, it's surprising, but turns out that the limiting TTL to 5 minutes for DS and DNSKEY doesn't change anything visible on the client. Another angle how to look at it is number of queries sent to the authoritative servers. So maybe we are hammering authoritative servers too hard now, but it turns out that it's not really the case. In the absolute numbers, the number of extra queries was 12,000, which is just peanuts if you look at the great picture. Because in overall increase in number of queries sent to the authoritative servers, were just 0.5% of the total volume, which is just, basically drawing in the noise. We were thinking, okay, this is really weird result. We were expecting something else. We were expecting at least some impact. So maybe we started worried that we are using weird data set, which is skewing the results. So we went chasing for different data source, and we've got a PCAP with traffic recording from a public resolver in the United States around the Washington, D.C. area. So completely different set of clients, completely different composition of query names. And most importantly, the top used TLDs in the United States are not really signed, or like not very much. Again, just to underline the point that we are using completely different data set. This is comparing the behavior of the clients from the telco and from the public resolver, and the public resolver is even weirder than the telco, as even weirder clients. So it's different data set. But turns out that two completely different data sets give the same result. On the US data set, the difference is so small that it's barely visible. I had to really zoom in the chart to actually see any difference between version of resolver with the TTL cap and without the TTL cap. So from the latency perspective, nothing changes no matter what data we try. So the only effect which is left is some increase on the TLD level for the DS queries. In our experiments, it was approximately 20% increase. And depending on the TLD, the DS query volume is like makes a different part of the total. So for CZ, it's like 8% of the total volume. For the GOOC TLD operated by Google, it's for some reason about 30%. So based on that, we can project theoretical increase if we lower TTL on all the DS records in the TLD completely. In theory, the projected increase in total query volume would be somewhere between 2 and 6% for the TLDs on the slide. For DNS key queries, we theoretically can do the same, extrapolation, but it's much harder to get the data out of the second level operator, so I'll not delve into that. So the question is it worth having 2 to 6% more queries on the authoritative servers on the TLD level? Is it significant even? And at this point, I will argue that it's not really significant, because it's maybe 6% increase in the steady state, or maybe 2% increase in the steady state. But the TLD steady state that's a trickle, right? My laptop down there on that table can handle ordinary TLD traffic for CZ, and it would just work. Because the reason is that the actual infrastructure is provisioned for denial of service attacks. So the steady state increase in the steady state is not significant at all from an operational perspective. Turns out that from the lab experiment, we've learned that there is no impact on the latency, absolutely minimal impact on the steady state, and the number of extra queries is really small. Now, the question is the experiment valid? And the only way how to find out is to verify in the real world. And turns out that the Google folks, headed by Viktor Duchovny, were lowering TTLs in their TLD called GOOC. They went from 1 hour DS TTL to 15 minutes. And it's already deployed for 1 month, so we can have a look at what happened. Here on the x-axis, we have dates. On the y-axis, total query volume as observed on the TLD level. And the red bars, the 2 red bars, are the days where they change from 1 hour to half an hour, and from half an hour to 15 minutes. And the yellow bar is kind of embarrassing part of the presentation, because turns out that after the experiment started and after they lowered the TTL for the first time, they realized that the accounting was incorrect, and some queries which had different letter case in the TLD label were not counted. So part of the increase on the right side can be attributed to the accounting fix. On the chart, you cannot really see any difference with naked eye. So here in the table, we can see that with 1 hour TTL and before the accounting fix, the DS queries were taking approximately 29 to 30% of the total query volume. And after the change to 15-minute TTL, it took 33%. So approximately 4% increase in the DS query volume. And that's really interestingly in line with the experimental results, because the experiment for this very TLD predicted 6% total increase if we were going to 5-minute TTL. They went only to 15, not 5. So the increase is not as high, but it's in line with the experimental result. Finally, some results I can stand behind. This chart is very similar and looks at the traffic on the second level. So we don't expect any difference here because they didn't change DNSKEY TTL, just DS, not anything and DNSKEY. And actually there is no increase, which is expected. It's just, changing query volume over time, but on the second level, the query volume for some unknown reason is not as stable as it is on the TL level. In the table, the table basically says that there is no difference on the second level. That's it. It's within basically rounding error. And we are at the end of the talk, so we can conclude that if we lower DS TTLs on the TLE level to 15 minutes, there will be no impact on the latency visible to the end clients, absolutely minimal impact on the TLE steady state, and no impact visible on the authoritative servers below the TLE level. So now the question becomes, why are we still having one-day TTL, and why are we making life very hard for operators who are possibly afraid of touching anything DNSSEC-related? Because if they make a mistake, they are stuck for 1 day or half a day until it expires. If it were 15 minutes or 5 minutes, the recovery would be orders of magnitude faster. That's all for me, and I'm ready for your questions.
Ralfi with Makamai, thanks a lot. Very fascinating talk. So 2 things that came to my mind. First of all, there wasn't a change in the name server record TTL, right?
That's correct.
That would mean that, at least curious for the DNSKEY, didn't go to resolution, which could have other effects. And the second is, did you look at the DNSKEY if there was a kind of noticeable impact on switching to TCP? Because, I mean, DNSKEYs are more often TCP than UDP.
Yeah, that's right. I have to admit, I didn't look at the TCP statistics, because when I saw that the overall increase is 0.5%, and that includes DS and DNSKEY as well, I didn't bother.
Okay. And can I beg you to do the stuff for the NS record?
Yeah, I will have a look. I have the data, so I can have a look.
Shall I go? This is Shimon Hart from Salesforce. So I'm going to follow up and encourage you to do the NS record thing as well, because we're also very interested in that. The NS record long TTLs cause the same problem, right? Because sometimes you want to be able to back out an entire DNS operator, regardless of DNSSEC. It could be related to DNSSEC. Maybe you move to an operator, they screwed up their DNSSEC, you want to back it out. You need to be able to have agility to change the operator fast, including the NS record set, not just the DNS record.
Understood. Yeah, that's for future work. Yes.
Yeah. And then the other comment I made. So you did this analysis. What are you planning? Are you planning to modify anything in Bind to deal with it, like clamp down?
Well,
TTL of DS or NS, or provide any knobs to do that if people wanted to do that?
Yeah. At the moment, there are no plans. The protocol says what to do, so we just follow the protocol.
Okay.
I think that this should be more like motivation for the TLEs or the customers of TLEs to push for the change, because the 2-day TTL is just unreasonably long.
Yeah, right. But I mean, I don't think you're, sorry, I'm dragging on a bit. I don't think you're violating the protocol by implementing a resolver side cap on a TTL. Resolvers can always do that. The TTL says you cannot keep it longer than that. It doesn't say anything about the other direction.
Yeah.
Okay. Thank you.
It will be short. So my comment is that we have TTLs that have a certain size for 2 reasons. One reason is to deal with essentially traffic loaded authoritative servers. The other reason is for resilience in the resolver end. And while this is great, it sort of assumes that you have perfect connectivity with your authoritative servers in parent all the time, which is not necessarily true in, well, parts of the world. So shorter TTLs are nice, but perhaps not in inner Africa.
Yeah, that's exactly the first slide, which is the TTL is always wrong. Yeah. Either too short or too long. Pick your poison. At this point, I will argue that TTLs are usually so over-provisioned that the risk of having them taken down by DDoS is much lower than the risk of the user or operator making a mistake and taking the domain down because of the DS record is incorrect. So that's basically my take on this.
Jim Reed, freelance consultant. I think the points that Johan has just made and the ones that Schumann made are perfectly valid and need to be taken a bit more carefully considered. I think it's not enough just to say, Peter, that because we see no increase in traffic, if you drop the TTL values, is a justification in and of itself to reduce the TTLs as a default stance. There are lots of other subtle factors that take play in this kind of scenario. I think the point I would like to reinforce is the one that Schumann made about the agility at the registry side of things. We all know for a long, long time that whenever you're going to change the mail servers for your domain, you'll drop the TTL on the MX records before the change and for a while after the change in case you need to back it out. It seems to me we're doing exactly the same thing with the NS records and with DS records, and I think a similar kind of practice would be best to be followed here, rather than say at a registry level, we're going to drop all the TTLs for DS records to 1 hour or whatever it might be. I think we have to be very careful making those kind of sweeping statements. And if we're going to look at this, we need to look at a lot more factors than just the query rates that hit the authoritative servers. Cheers.
Yeah, I generally agree. The problem is that the more logic we add to the mechanism for changing records, then the more unpredictable or harder to understand for other people it is. But I agree that dynamic TTL on the records might be also an option.
Yeah, I mean, the fact is, I think the end client, or in this case, the domain name holder, really needs to be signaling to the registry that they're going to be making a key rollover, in which case then the DS record values and the TTLs are much more significant. And I think that's the issue we need to tackle, rather than look at it in terms of all these other things. I take your point about the fact you're going to add maybe a little more complexity on the registry side of things, but they've got the resources to handle that in the way that the end clients definitely don't.
Yeah, I wish it were true, because if we were in the perfect world, we would use EPP to actually change the TTL, but so far that didn't happen for a couple of decades, so I'm not holding my breath.
Last question is for Rick.
I'll be very quick. Rick Wilhelm, PIR. I just threw a link into the Mattermost chat. It's a link to a draft from Gavin Brown that it's something that a few of us have been talking about for a while, that allows the manipulation of TTLs over EPP. I'm not sure if you'd bumped into it in your research on this. This is, I want to also call out some discussions and give credit to some thought work by Victor Duchovny, who's one of the people that's been pushing for something like this due to some comments that related to comment that Schumann made about stability of when you introduce changes to DNS. Schumann knows all about this. So anyway, so that's in the Mattermost chat. Probably maybe worth a check out. It's like everything in the IETF, it's discussed in the list. I think there might be time for it in Hamburg. If anybody happens to be there, hopefully you can participate in regex. Thank you.
Thank you.
Yeah, thank you, Petr.